In this section, we discuss the definition and interpretation of the normal force. The normal force is one component of the force that a surface exerts on an object, namely, the component that is perpendicular to the surface. There are many situations that you will encounter in which an object, such as a concrete block, is in contact with a surface, such as a tabletop. Because of the contact between their surfaces, a force acts on the object. One component of this force is due to friction and acts parallel to the surface of contact. The other component is directed perpendicular or normal to the surface and is called the normal force. Consider the concrete block resting on the table. The block is subjected to gravity and therefore to the force of weight and would accelerate downwards to the floor if there were nothing to balance the weight. The normal force has exactly the same magnitude but opposite direction as the weight of the block. It provides exactly enough force to balance the weight. But what is the origin of the normal force? You can get an idea of the nature of the normal force by considering what happens when you sit on a mattress. Your weight causes the springs in the mattress to compress. As a result, the springs exert an upward force on your body. This is the normal force. In a solid surface, such as the tabletop, you can imagine a similar situation where the bonds between the atoms compress, although imperceptibly, much like the springs in the mattress, and thus produce a normal force on the block. Newton's third law plays an important role in connection with the normal force. In the case of the block on the tabletop, the table surface exerts a normal force opposite in direction but equal in magnitude to the force of weight applied by the block. The reaction force of the table surface to the weight of the block, in the context of Newton's third law, is the normal force. If other forces in addition to the weight and normal forces act in the vertical direction, then the weight and normal forces are no longer equal. For instance, if a block weighs 15 newtons, then, if no vertical forces other than the weight act upon the object, the magnitude of the normal force is 15 newtons. However, if someone pushes vertically downward on the object with a force of magnitude 11 newtons, the normal force must increase to 26 newtons in order to compensate. Similarly, if someone pulls vertically upward with a force of 11 newtons, the normal force decreases to 4 newtons. This makes sense. If the magnitude of the pulling force were equal to the weight of the block, then the block would essentially be suspended by the rope, and the normal force would be 0. It is important to understand that the normal force acts perpendicular to the surface, even if the surface normal is not vertical. In the case of the inclined plane, for instance, the weight vector acts vertically downward, but the normal force is directed perpendicular to the plane. In such a case, the magnitude of the normal force must be equal to the component of the weight vector that is perpendicular to the surface of the plane. You will encounter numerous other situations where the normal force is not vertical. We now discuss a situation that arises that involves accelerating objects, the concept of apparent weight. Have you ever experienced your knees flexing slightly when riding an elevator that accelerates upward? Do you feel heavier for a second or two? You should, because your apparent weight has increased slightly from your true weight, which is just m times g. Suppose you were standing on a scale in the elevator. The scale would read a larger value than your true weight when the elevator accelerated upward. Your apparent weight is equal to the normal force between your feet and the scale, and the scale reads the normal force. How about when an elevator accelerates downward? Ever experience a queasy feeling in your stomach for an instant as if you were starting to fall? Your apparent weight, in that case, is less than your true weight, and the scale would read a value less than your true weight. Now, what if the cable broke and the elevator accelerated downward with a value of g, the acceleration due to gravity? What would the scale read then? It would read 0, and you would be experiencing free fall, which feels like weightlessness. This means, of course, that your apparent weight would be 0 in this case. We now analyze the apparent weight problem using Newton's second law for the case of the elevator accelerating upward. The true weight, that measured on the scale when the elevator is not accelerating, is equal to m times g. In reference to the free body diagram, the sum of the forces in the y direction is equal to Fn minus mg, which is equal to m times a. This means that Fn is equal to mg plus ma, or the apparent weight equals the true weight plus the mass times the acceleration. Therefore, the apparent weight is greater by an amount ma than the true weight when the elevator accelerated in the positive y direction. Note, if the elevator accelerates downward, the sign of the last term, ma, would be negative. So you can see directly that if this last term were negative mg, the normal force, or the apparent weight, would be 0. The important concepts of this section are the following. A normal force acts between two objects when they are in contact. The normal force does not necessarily have the same magnitude as the weight. The value of the normal force depends on what other forces are present and also on the angle the weight vector makes with the surface, as in the case of the inclined plane. And finally, in the case of accelerating objects, such as the elevator example, the apparent weight is given by the magnitude of the normal force.